Yes. So I would like to start by saying what our work is not. And indeed, it's not a predictive scenario giving a trajectory to follow to reach given energy landscape in 2050 and resulting from a continuous evolution from the present situation. This is not at all this type of work. In fact, our initial motivations were to describe quantitatively what could be a world energy landscape in 2050 under very specific constraints that we have chosen at the very beginning, which are a finite amount of total energy, a reduction of greenhouse gas emissions, and also a reduction of inequalities of energy consumption in the world. And the aim was to determine quantitatively the impact of all these constraints on the energy consumption per capita for different types of populations and the energy mix allowing a good match between energy needs and the available sources. So for this presentation, I will focus on our working hypothesis, the different parameters that we have used, and I will give some example of outcomes or results to see if this work can be adapted to be used as a tool to analyze different scenarios under these constraints. So the first working hypothesis concerns the inequalities of energy consumption that we assume to persist in 2050. And to describe these inequalities, we have assumed or considered that they will exist within a given country. It means that within each country, different types of population can coexist, having different energy consumption level, typically high, moderate, and low consumption. And this is what we have considered for emerging and poor countries, which describe the population of these countries is described in 3 categories of population, as I mentioned before. And we assume that in the present developed country, all the population were in the group P1 with high level of consumption. So this description of these inequalities means that all the CIs, C1, C2, and P3, are the same whatever the country or the region that we consider. And if we make the sum of the P1, P2, and P3 in each country, and we sum over all the countries, we obtain the value of this population at the world scale. And what we know is the energy consumption of each group of population at the world scale. The sum has to be equal to the world energy demand. So this is the strong relation that we use, the first relation. The second point is we have chosen to parameterize these inequalities of energy consumption between PIs with a unique parameter named alpha, which means that, for example, the richest population, P1, consume alpha more energy than P2, which consumes alpha more energy than P3. So with this parameter, we can parameterize the world energy demand through alpha, the different PIs at the world scale, and the energy consumption per capita, C3. So it's very simple. In our approach, we have fixed the world energy demand, the parameter, the inequality ratio alpha, and the values of P1, P2, and P3 at the world scale. to obtain as results the absolute value of C1, C2, and T3. So, of course, because of the simplicity of this relation, we can switch parameters and outcomes with each other. But in our approach, we needed values of PIs. So to obtain these values, we have parameterized the PIs, the different group of population. And to do that, we use the urbanization rate because we consider that there is strong correlations between urbanization, economical development, and so the energy consumption. So from this urbanization rate, which can be extrapolated up to 2050, we can determine for each country the urban and the rural population. And the purpose is then to distribute this urban and rural population into the different category P1, P2, and P3 that we can parameterize in this manner. So again, we've made some assumptions, and the first one is to consider that urban populations will live in cities, will have high and moderate energy consumption. And the second hypothesis is the rural population will have mainly the lower energy consumption. Of course, we can adjust all these parameters to distribute urban and rural population according to the economical development of the country. And for example, in our reference case, we have assumed that in emerging countries, as China or Asia, half of the urban population have high level of consumption, and the other part has a moderate energy consumption. And at the opposite, in poor countries, like in sub-Saharan Africa, all the urban population have only a moderate consumption energy. And in our description, in our reference case, we have also assumed that all the rural population mainly has the lowest energy consumption level. But again, this parameter can vary. So here on this figure, I show you the result that we obtain in terms of P1, P2, and P3 population for different countries or regions with this set of parameters. And the value of P1, P2, and P3 at the world scale are these one. And for example, we see that the distribution of P1, P2, and P3 in China and India is quite different because, for example, the urbanization rate is much lower in India than in China. So with the same rule of distribution, the fraction of rural population in India is much higher than in China. And this is what we can see here. I am clear? Okay.
What's GINHAB?
Sorry?
GINHAB?
Giga inhabitant. Sorry. Billion, when we say billion of inhabitants. People. It's a physicist unit for... Sorry. Okay. Yes, so in our reference case, we have fixed the world energy demand to 20 gigatonnes per year, and we have fixed the inequality ratio alpha equal to 2, which represents a reduction of inequality compared as today by a factor 2 between the richest and the poorest population. And knowing the value of P1, P2 at the world scale, we can then deduce the absolute value of the three levels of consumption and then deduce the energy consumption by each category at the world scale. And as we know the composition of the population of each country in terms of PIs, we can deduce the energy consumption per capita for each country or region. And this what I have represented here in red, and we can compare this energy consumption with the present one. And for example, in this reference case, we observe a reduction of the consumption in present developed country by 25%. And because of the reduction of inequality, we see that in poorest countries, we have increased the energy consumption per capita by a factor 2. But we see that also that it's nevertheless time for smaller than the richest population. So maybe we can consider that it's not really satisfying. With this simple relation, we can also observe the evolution or the variation of the different CIs with the world energy demand, with the PIs, with the inequality ratio. And here, for example, I have represented the evolution of C1, C2, and T3 with the world energy demand. And for example, we see that if we want to maintain in 2050 the mean energy consumption of present developed country, which is around 4.4 TRE per capita per year, with a reduction of inequality ratio, we see that we need to go up to 20 gigatOE and towards 25 gigatOE per year of world energy. And at the opposite, at 15, we see, for example, that it's not enough to poor and emerging country to increase significantly their energy consumption. We have also evaluated the sensitivity of DCIs with PIs, and in fact, the sensitivity is rather small. And here on this figure, I have represented the relative variation of the CIs as a function of a relative variation of the richest population P1, which is the case where the variation is the most important. And for example, we can see that, again, to maintain the present mean energy consumption of developed countries in 2050, we see that we have to reduce the richest population as much as possible, typically 50% from our reference case, to maintain this level of consumption. And to end, I will show you the evolution of these CIs, the relative variation of these CIs with the inequality ratio alpha. When alpha has high value, it means that we go toward higher inequalities. Today we are, the inequalities between richest and poorest countries are around 3. And our reference case, I remind you, it's alpha equal 2. And the variation for the population P1, P2, and P3 are the following. And we see, for example, that the poorest population are the more impacted by these inequality ratios because their relative variation are much more important than the other. Now, again, if I decrease the fraction of people who can reach the rich population by 25%, of course, we can increase the value of the energy consumption per capita. And again, if we want to maintain the present energy consumption of developed countries in 2050, we see that we have to reduce the part of the rich population and to have an inequality ratio rather high. Now, the third working hypotheses concern the greenhouse gas emissions. And in our reference case, we wanted to take into account the climate constraint. And of course, it represents a limitation of the use of fossil fuel leading to CO2 emissions. And as previously, we have wanted to determine the amount of fossil that each group of population can use in 2050. And as previously, we have also made the choice of a unique parameter to describe the inequalities on the fossil fuel consumption between the different group of population, P1, P2, and P3. And this inequality ratio on fossils, named beta, is beta. And again, we can parameterize the total fossil fuel with CO2 emissions as a function with beta and the PIs at the world scale and the fossil fuel consumption F3 for the group P3. In our reference case, we have fixed the total fossil fuels with with CO2 emission to 4.2 gigatonnes per year, which represent a reduction of greenhouse gas by a factor 2. The value of beta is smaller than the value that we have chosen for the inequality ratio on energy consumption. It means that we have reduced the gap between fossil fuel consumption between these three types of population. And it means also that we have reduced these inequalities on this fossil consumption by a factor 6 compared with today between the richest and the poorest population. So from these parameters, we can obtain the fossil consumption for in TOE per capita per year for each group of population. So we can determine the fossil consumption for P1, P2, and P3 at the world scale. And again, as we know the composition of the population of each country in terms of PIs, we can obtain the fossil fuel consumption for each country or region and deduce the CO2 emissions in 2050. And this is what I have represented here in green, light green. So a ton of CO2 per capita per year, compare as today here in black. And as we all know, the climate constraint and to reduce CO2 emissions are very difficult to, it's a target very difficult to achieve. Because, for example, we have to reduce in developed countries by a factor 6 the CO2 emissions. For the last part, I will focus on the match between available sources in 2050 and energy needs. And this question has to be addressed in the case where we reduce significantly the use of fossil fuels. So we have to quantify first the energy demand, and of course, on the other side, we have to quantify all the available sources and the CO2 non-emitting sources, and to see if they can match the energy needs. So we have considered 4 consumption sectors: transport, industry, which means high temperature heat only, residential services, where the needs are low temperature heat, and electricity. And we also we have also considered that these 3 groups of population, citizens and rural, will have different profile of consumption. So we have built an average consumption profile which represents the fraction of the total energy which is used in transport, residential services, industry, and electricity from the present developed countries, emerging countries, and poor countries. And from this average profile, we have attributed each profile to the P1, P2, and P3 group in 2050. So we have transposed the present profile to 2050. As we have the energy consumption for each group of population, and with the profile of consumption, we can determine for each group the energy in each consumption sector. This is what I have represented here. After we count the available sources, so we have considered fossil fuel with CO2 emission fixed by the reduction of the greenhouse gas related to fossil. We have considered main renewable energy sources, and we have also considered the use of fossil fuel with CCS technology and nuclear power. In our approach, we have fixed all the potential of these energy sources. For example, we have fixed for CCS technology 3.7 gigatons per year, which represent 12 gigatons of CO2 to store each year. And, And for example, for renewable sources, we have taken, the potential of these renewables can be extracted from different different technico-economical models. But in our case, we have chosen the potentials given by the WEC, the World Energy Council. And for nuclear power, we let this energy as free parameter. All the others have a potential fixed, but nuclear power is used as free parameter. And for each energy source, we have the potential in 2050, and we also analyze what kind of needs each source can provide. And from this set of parameters, we built the energy mix of each group of population, and we deduce the energy mix for country, region, and at the world scale. So I have time or what? I don't know.
That's okay.
It's okay? Okay. So I'm going to rapidly present you our methodology to construct this energy mix. Donc first, we start from the needs of each group of population and in each consumption sector, transport, industry, residential services, and electricity. And we start our construction by fossil fuels with CO2, because this consumption is fixed for each group. And as the CCS technology is very difficult to implement for transport, thank you, we decide to use around 80% of this consumption with CO2 emission to transport. And the rest is distributed into the other sectors in proportion of the needs. In a second step, we use renewable energy sources for transport and heat. And there is a specificity for biomass that we dedicate mainly for rural population here in P3, as is the case today. And so half of the potential of the biomass is for the rural population, and the rest is distributed into P1 in P2 for transport, for heat, for it, in proportion of the energy missing, meaning that the energy which is not provided by the fossil fuels with CO2. At this stage, we see that a large part of transport is not provided by energy sources, so it has to be transferred to electricity as electrical transport. And in our case, it represents 35% of the total transport needs. And for industry and residential services, to avoid a direct transfer to electricity, we choose to use cogeneration to produce simultaneously heat and electricity. And for that, we use fossil fuels with CCS technology for the heat needs. And again, a lot of energy is missing. So we have thought to use nuclear for direct production of heat. And of course, the nuclear power, we have assumed that it was mainly used by P1 and P2 populations, and which can be well adapted for industry needs. And at this ultimate stage, we see that some energy for heat is missing. So at this stage, we have no more other possibility than the transfer to electricity. So now we focus on the electricity, and I remind you that we have in blue the classical uses of electricity, and in red the transfer of heat and transport on electricity. And so the production, the electricity generation increased a lot because of this transfer. And we have also minimized this transfer by using cogeneration, as I showed you before, and by using, for example, heat pumps. From the previous steps, a very small part of electricity is coming from fossil fuels with CO2 emission, biomass for P3, and electricity coming from cogeneration. So after we use renewable energy sources for electricity generation, again in the proportion of the energy missing, of the electricity missing, we use again fossil fuels with CCS to produce electricity because the needs are quite huge. And at this stage, we reach the potential that we have fixed at the beginning. And at the ultimate step, we use, nuclear power to fill the energy missing. Yes?
Sorry for this my question, but CCS is obscure for me, so CCS is what?
Carbon
capture,
carbon capture and storage. Sorry. Capture and storage carbon. So we can use fossil fuels. But by capturing the CO2 and to store in the land, we can use fossils and preserve the climate with no emission of CO2. Okay, so the kind of results are the following. First, we can have the energy mix of each group of population, P1, P2, and P3, and their energy mix are quite different because they reflect the hypothesis that we have used and the values of our parameter on inequality ratio on fossil fuels. For example, we see that the biggest part is for the rural population. We see also the part of biomass, which is important, And we see also that nuclear energy, nuclear power, is mainly used for P1 and P2, which are citizens, for which the needs are very concentrated and much more important. From this energy mix, we can deduce the energy mix of different country and region that I have represented here. And we can, of course, deduce this energy mix at the world scale. From these results, we can also focus on electricity and observe the ratio between intermittent electricity and the total. This is what I have represented here in black. But we can also compare the intermittent electricity with only the flexible sources. And in that case, we reach 50%, meaning that we are far above what we are able to do, which is around 20%. So we see the interest to make some energy sources more flexible that they are used to be, yes, as nuclear power, for example, or CSP, or concentrating solar. And we can also obtain the distribution of nuclear power at the world scale. So in the reference case that I show you here, we have nuclear power multiplied by a factor 9. Let's compare us today. And we see that, for example, in 2050, the nuclear power will be implemented essentially in Asia, where the production overshoot the one in developed countries. But we can also look this energy production per capita, in kilowatt hour per capita per year. And we see that it's varying from 1,000 to around 4,000 kilowatt hour per capita. And I would like just to remind you that in France, the French case corresponds to 7,000 kilowatt hour per capita. So France is somewhere here. So the results are quite below the French case. I'm going to conclude. So I would say that we have made the choice to use simple relations and using fewer parameters as possible. And from this simple relation, from this simple parameterization, we can switch parameters and results. So it makes more flexible the use of this work to project different scenarios through the chosen parameter. So maybe it's a good point. The second point is that we can interpret different scenarios in a common framework based on inequality ratios. We have fixed at the beginning the choice to describe the world as inequality ratios of energy consumption and CO2 emissions, or by considering different types of population. And this consideration can be interesting to analyze the issue on climate negotiation or on the resource sharing, for example. So it is important to know how much each country or region is going to consume and how many tons of CO2 or fossil fuel they are to consume or emit. The analysis of the match between energy sources and energy needs and the corresponding mixed energy construction reveals some critical problems related to the climate constraint. as for example, a lack of energy sources for heat and transport need, and the increase of electricity, not only because classical users increase, but because there is a massive transfer of these needs, transport and heat, on electricity. The simplicity of our approach can also analyze the correlation between initial hypotheses used in scenarios and to observe the possible contradiction between these hypotheses. For example, it seems very difficult to conciliate development of a poor and emerging country plus a reduction of greenhouse gas emissions and plus no nuclear power, for example. And for us, it was also important because we can analyze how all the different energy sources can compete with each other and impact some key points as electrical transport intermittency or CO2 storage capacity. Thank you.